which is anything up to 500 kilowatt. Okay, it could be IGBT or MOSFET. Then the higher power one, those with that are actually more than 500 kilowatt, we may need to switch to other type of devices. For example, the IGBT, thyristor, and so thing. Yeah, as the power is actually goes up, you can see that their frequency that you can use to switch the switches, it will become lower. Yeah, because normally high switching and power is always proportional inversely. Yeah, so power high, the switching frequency will be low. Yeah. Now, when it comes to the ideal switch characteristic, you can see that there will be 5 characteristics here. Okay, so the first one is there will be no limit on the current flow, because ideal switch, we assume that it can work at any value of the current up to infinity when the switch is actually turned on. Yeah, and there will also be no limit of the this device voltage. Okay, when the switch is actually turned on. When switch is turned on, so you do not need to have some sort like a voltage drop across the given type of the material, the given type of the switch. Okay, for example, silicon type of switch, you need to have a threshold voltage of 0.7 or 0.6 in order to turn it on. But ideal case, no. Okay, and also there will be no voltage drop. Okay, when the switch is on. Okay, they will also be having the infinite off-state resistance, so that when the switch is off, there will be no leakage. Yeah, meaning that you have infinity of this resistance. Okay, and the last one is that because of the switch is classified as a type of ideal switch, that means that there will be no what is so-called the transition time from the off to on time, and also from the on to the off period. So theoretically, you can say that there is no limit to the switch. You can say that the switch is 10 gigahertz or maybe more, 100 gigahertz also can. You can use it, but in reality, those devices is actually limited by the speed, the operating speed limit. Okay, due to there is actual traveling time in between the on to off state, and also off to on state. Yeah. Now, when it comes to the practical switch, things are different. So that is why before I switch to the practical switch, you look at this ideal switch. That is why when we are talking about the ideal switch, the characteristic is that final conclusion is that there will be no power loss. Okay, when you are looking into the last graph, there is no power loss under this power versus time graph here. Okay, but when it comes to the practical switch, things are different. There are some characteristics. For example, there is a limited power handling capability. So that means that each given switch or device, they are having their maximum possible voltage and the current that they can actually go. Okay, so it's no longer infinity, it's just limited. Okay, then the second one is the switching speed is also limited because of the traveling time needed for the switch to turn from off to on, and also from on to off. Okay, that is why it limits the frequency, the switching frequency that that is actually used to that particular switch. Yeah. Also, there is a finite on-state and off-state resistance. That means that when the switch is turns on, there is a small resistance, which is opposed to the ideal switch. There is no resistance during the switch is turned on. Okay, so when the switch is turned on, there is a small resistance, which is we have already discussed during during the Monday class. So you can see that when the switch is on, there is a on-state resistance, or this on-state resistance normally I call it as a on-time resistance, RDS on. Yeah, RDS on. Okay, so different switches or different devices, you provide you with different amount of this resistance. The lower is better. Why? Because lower it allows more current to flow through. Yeah. And also during the this off state, during the off state, for the ideal switch, it tells you that the resistance is infinity. But when it comes to the actual this switch, the offset, they do also have its limited resistance. Okay, be it say 1 megahertz, sorry, one mega ohm, be it like 1 mega ohm. That means that 1 mega ohm is still a value. So if you have this voltage applied across it, then you can see that there you also have a small amount of this leakage current. Okay, and because of the characteristic of number 2 and also number 3, that actually make up the characteristic of number 4. Okay, so you can see that there will be this losses. There will be a losses appear to your this practical switch, especially when the switch is from turn off to turn on, and also from turn on to turn off. So these two regions here is what we so-called the switching loss. Okay, switching losses. Okay, and we do also have another loss, which is termed as conduction loss. Conduction loss can be happen during when the switch is turns on, and also when the switch is turns off. Okay, when the switch is turns on, as we have already said that there is a finite state of resistance, so there is small amount of resistance, so that there will be also P, I and the V, and hence you have the P. So that P is then the conduction loss during the on time. And during the off state, there is a limit. There is a limited amount of this resistance, even though it's large, but there is a value. If there is a value, there is a current, and the current is low, but the voltage is actually high. When off, you measure the voltage, right? Okay, so you also have this so-called the off-state conduction loss. Yeah. So far, okay, huh? All right, so thank you. Okay, then we continue to this power diode. We look at those numbers. Okay, this one could be very fast. All right. Now in the power diode, normally you are having a symbol like this, and then if you are looking into this slide here, in fact, a diode is actually formed by the PN junctions. Okay, a PN junction make up the points as one as anode and the other one as a cathode, so that when there is electricity applied to the diode, then there will be a current flow through. Okay, so power diode normally can handle up to 5,000 and up to 5,000-6,000 of voltage. Okay, so depend on the category and the range. So the switching speed is somewhere in between as low as 100 milliseconds and can be up to as fast as 20 nanosecond. Okay, so as you know now, when you are looking into the large amount of this time, that means that the switching speed is low. If it, mainly this kind of switches having a very high rating. Okay, if it is small in time, that means that the switching frequency is high, and you can see that their rating should be low. Yeah. Now, for a given diode, yeah, typically we can actually make model. We can model this power diode into three types. The first one is called the ideal model. The ideal model is just like this. Okay, so during when the switch is in when the diode is in forward bias, we can just assume that this one is just a mechanical switch that are connected to from this point K here to the point A here to point K here. So there will be a current flow through. Okay, and also when the switch is actually in its off state, so we just open the switch here. And hence, when you are plotting the IV characteristic, you can see that this is the IV characteristic for the type for this type of ideal switch. Yeah, very simple. But this one is not really close to the actual or the practical diode. So you may want to add something to make it more close to a practical one. So the second model is called the barrier potential model. Barrier potential model is in such a way that I'm adding in a reverse small battery to the circuit, so that when during the on state, so I will need to overcome this small voltage only, then this diode will then be conduct. Okay, and hence you can see that there will be a slight what to call it, the voltage drop, small voltage drop before it can turn on. And during the off state, it's the same. You just make your switch, your this mechanical switch to be open, so that your this characteristic, IV characteristic, is something like this. And this one also not very close to, okay. Of course, this value 0.7 is actually for a type of this device that are made from silicon material. Okay, if we are using germanium, for example, this value could be just 0.3. Yeah, okay, different type of material determine the threshold value needed, yeah, for the device. Then the third one is a more complete model. Okay, complete model is more accurate. How accurate is that? Instead of putting a switch here, then I'm actually include the series resistance. This RD is small capital D here, is actually used to model the diode when it is in forward bias condition. So this can actually help you to limit the current it flow through. So the current no longer actually infinity. So it has some sort of this limit. Okay, and also when we are having this diode is actually turns off, the switch is actually turned open, but we have this additional reverse resistance RR here connected in parallel to the switch. And so this is to actually tell you that even though the switch is open, there will be a small resistance, okay, a limit value, okay, or the finite value of this resistance connected in these 2 points, and hence there will be a leakage current. Okay, so when you are looking into the IV characteristic, you can see that the IV characteristic is something like this. Okay, more realized. But of course, this kind of switch cannot be modeled when you are talking about the avalanche and all those things. Okay, then this model may not really work for you. But at least, okay, for normal operation, you are not actually apply your diode in working under this so-called avalanche region or conditions. So this should be good enough. Okay, so this circuit, this equation here is actually called the Shocky diode equation. Okay, ID is your the current. I8 is your leakage or the saturation current. So you have this equation for you to calculate what is your actual direct current ID. And we also have this so-called the VT here. The VT is called the thermal voltage. The voltage here, you depend very much on the temperature that the diode or this device is actually have. Okay, different value of this temperature you give you different value of thermal voltage VT. K and the Q is actually constant. The Q is in fact your charge. Okay, we have a constant value, and then the K is actually the Boltzmann's constant. Okay, T is the temperature in Kelvin. Okay, so when you are looking into this, the VT will actually vary according to the temperature T only. The Q having this value, K also having this value, which is a constant. Yeah. So for temperature in Kelvin, how do you actually convert from a given, say, 37 degree into Kelvin? 37 degree, what is the value in Kelvin? Anyone can answer me? 237, not 235. Okay, 235 plus 37. Okay. Okay, so you are quite correct lah. You need to add the 237 in value to convert into Kelvin. Yeah. All right. All in all, a diode characteristic basically can be divided into these three regions. Forward bias region, meaning that your diode voltage VD is greater than 0. Reverse is the other way around, so less than 0. And breakdown region, that means that your breakdown voltage will be should be actually greater than your this diode voltage. Yeah, the forward bias voltage. Yeah. So and of course, when it comes to a reverse bias region, your this ID somehow actually change, because you can see that you can see that this term become very small, and hence you can see that your ID is in fact approximately equal to minus IS. Okay, the saturation current, reverse saturation current. Yeah. And this one just tells you an example to find the saturation current IS. So give you the VD 1.2 volt, ID is 200 amp, and emission coefficient is 2, and the VT is 25.7 millivolt. So thermal voltage provided to you, don't need to find it. Okay, so just need to apply this formula, and then you found that your IS is equal to this one. Okay, typically this saturated current is actually a reverse current. It normally is very small, in nano or maybe possible in micro amp range. So if you calculate your reverse saturation current is very high, something wrong. So you need to actually rework. Okay, so this common sense. Okay. And also for the this power diode, we do also have one this thing called the reverse recovery. Now you know that when the diode is actually try to turn off, okay, you won't actually goes off and then sit on this horizontal line, but instead you actually go down beyond the horizontal line, the 0 line, and then go further down, and it takes some times, only then you turns off. So this time here, starting from here until it reach the the horizontal line here is called the reverse recovery time, TRR. Okay, this determines how fast your diode to actually respond. Okay, the effect of this reverse recovery can be actually cause the switching losses to be increased. Yeah, and also they'll have some kind of this voltage spike. Okay, the spike in when there is the inductive load is actually used. Okay, now basically we have two types of recovery. One is called a soft recovery, the other one is called the abrupt recovery. Okay, soft recovery, that means that you allow the this time to have longer, so that your this diode will actually turns up slowly. Okay, so but it take longer time. This is not advisable. Okay, okay, and that's why there is another one is more aggressive one called the abrupt recovery, and you can see that the time needed is actually a lot smaller. Yeah, as compared to the soft type. Yeah. So, and all in all, the TRR can be actually equal to two components, which is your TA plus your TB here. TA is actually the time here when the switch is about to turns off and it hit the horizontal line. The first time it hit the horizontal line before it completely turns off. And then this time is actually determine how much the this IRR, the maximum current that it hit the IRR point. Okay, this is called the TA. Then the TB is actually the time that taken from the maximum value go down to the 0 point. Okay, TA plus TB. Okay. The ratio of TB over TA is known as the softness factor. Normally we call it as a SF. Okay. You do also have this the peak reverse current can be expressed in reverse DIDT as in this equation number 2 here. So the IRR can be equal to TA times your DI over DT. Yeah. So from there we can see that the charge QRR can be then approximately equal to half of the IR times TA plus half of the time times IR times TB, and hence you have equation 3 here. Yeah, half of it, half times IR times TRR. So if you are actually do some kind of this arrangement, you can see that your IRR somehow is approximately equal to 2 QRR over your TRR. And hence, from the equation 2 here, and also the equation 4 here, you can actually obtain equation 5. Okay, if we are actually ignore the TB normally is small if we are actually consider the this abrupt type. Don't consider this one. Normally we want the reverse recovery to be small, and when you are looking into this abrupt type, they will have some what is so called some sort of this ringing across your this horizontal line, but it is small enough to ignore, and hence this TB here, the time will be much smaller than the TA. Okay, and hence we can then say that the TRR is almost approximately equal to your TA, and that is why we can TRR can be further reduced to approximately equal to the equation number 6. And if you do some sort of substitution, we can find that my IRR is then equal to equation number 7 here. Yeah. Okay. So this one is not not much big deal, just to tell you some history and all those things. But at least you know a little bit of it. Okay, we are not really using it. Okay, but at least you know. All right. In this example 2 here, to find the reverse recovery current, it tells you the TI is 3 microsecond, the rate of flow of diode, this is called the DIDT, which is 30 amp per microsecond. You want to find the QR and also the IR. So this question can be solved easily by applying equation 6. You got the QR. Equation 7, you can obtain the IR. Yeah, very straightforward, right? I hope everything is okay for you, for this part. And then when it comes to this thyristor or the SCR, they are a little bit different. As you can see that when you are looking into the symbol here, the symbol, you have additional getting pin here, or the getting this lead. Okay, so it actually formed by how many PN junction? How many PN junction does SCR have? How many? 2. 2. Correct or not? 2. 3. 2. Wow, so many 2. So many 2. Got 2, 3. No 4. No 5. 10. Oh my goodness. How you count? How you count? Zhi Yuan, got 10. How to count? So from here you see you have 1 P1, N1, P2, N2. So PN junction, how many PN junction we have? Meaning that this one is 1 PN junction. This one is another PN junction. This one is another PN junction. So for a given thyristor, they are in fact having 3 PN junction. Okay, not 2. I know why you count 2, because you count this one is 1 and this one is 1, and you forgot the one in between. So basically there are 3 PN junction for a given thyristor. Okay, this one tells you the what do you call it, the actual, not the actual, this one is the ideal type of thyristor. Okay, so this one you also can use the similar method that we do the modeling for this diode to model it, and then this one is the actual one. So typically thyristor and diode having quite similar of this power rating typically, but just that thyristor need something to trigger. Okay, this something is actually the tiny current pulse. Yeah, you need a current pulse to apply to this gate. Only then you allow the current to flow from anode to cathode. That's it. Yeah. All right. Triac is called the triode for alternating current. Nothing much. Triac is in fact, yeah, a 2 thyristor connected in anti-parallel way. We common getting pin. Yeah, the getting pin is actually connected. So regardless whether you are applying both the thyristor getting pin at the same time, only one can turn on. Why? Because mainly this kind of triac is only work for, it is mainly work for the AC lah. That is why when during a pulse-up cycle, say this one is pulse-up cycle, current flow from anode 2 to the anode 1 here. So only then this thyristor will then be turns on. This one is reverse blocking, even though it provide the getting pin is blocked, so it cannot flow through this part. Only flow to this part, and only wait until the next half cycle, the current direction change. So the current is flow from this direction. Only then this one is working. This one is turned off by itself. Okay. So triac normally having a very low this power rating. It could be up to a few hundred watt only, and the maximum current that it can go could be few tens, maybe up to 50 amp only. So mainly this type of triac is actually suitable for home appliances and some hand tools. Yeah. GTO is termed as the get turned off thyristor. So it's opposite to the this thyristor. Thyristor can only turn on, but it cannot turn off. Okay. Once you want to turn on another time, you need to wait for the next cycle. Okay, to turn it on. Yeah. If you have a alternating current to the diode, so during positive cycle it work, during negative cycle it won't work. So you need to apply another type pulse to the gate, only then it work. And this one GTO is different. Okay, you can see from their this layout. Okay, and also when you are looking into the symbol here kind of similar, but just that there is another line here, tiny line here. Yeah, as compared to this. Okay, so that makes a difference in between the symbol. Okay, GTO it work in such a way that it can allow you to turn on and also turn off the thyristor. Okay, if you don't want, you just apply another reverse pulse, negative pulse to it, to the gate, then you turn off. Okay, so this is a kind of fully controlled device. Yeah, then SCR is a kind of semi-controlled device. Yeah, that makes a difference between the two. Yeah, normally this kind of thyristor is actually used for any rating that are more than 100 kilowatt. Okay, yeah. We do also have this power BJT. Now, power BJT is a type of current control type of device. Okay, as we know that it required the 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 base to be actually connected to a source. Okay, so we have, for example, we have this CBE type. Okay, this type is a type of MPN. This one is PMP. Okay, so as long as I have a VBE appear, okay, across these 2 points, then there will be a current. The transistor can then be turned on, and then there will be a current to flow through from the collector to the emitter. All right. But that amount of current that flow through, flow to the collector and then go through to the emitter is actually depends very much on the current that you are apply into the base. That means that the IB that actually matter. Okay, the higher the higher the value, it allow more collector current to be flow through. Okay, so that is why it's a type of current control type of device. Okay, BJT normally can go up to 1,000 plus of voltage in rating, and also few hundred amp in its current rating. Yeah, the switching speed is considered okay. You can switch to a in terms of kilohertz type of this speed. Yeah, not too bad. Can also handle quite high amount of this power rating, but just that it's actually a type of current control type of device. So current control sometimes in terms of control, normally we are more like to use the voltage control type of device rather than current control type. Okay, difficult for this for you to control the current, but voltage is a lot more easier. Yeah. Then we do also have the MOSFET or MOSFET. Okay, a MOSFET we have gate drain and also the source. Similar to the BJT, yeah, as long as there is a getting pulse applied to the this getting pin, or we have the voltage across the G and S. So we have the VGS. As long as we have the VGS, then there will be a current to flow through. So the amount of current to flow through is actually determined by how much the VGS that you have. The higher the voltage that you apply to it, okay, then the more current is allowed to flow through from the drain to the source. And hence you can see that MOSFET or the FET is a type of voltage control type of device. And BJT, BJT and this MOSFET is also a type of fully controlled type of device. Yeah, you want to turn it on at any time, and you want to turn it off at any time, also can. Yeah. MOSFET normally work in higher frequency as compared to the BJT. So this is the strong point for the MOSFET. However, the power handling capability is not as high as compared to the BJT. Yeah. So typically you can see that it may be able to work up to 1000 watt, but the current that it can actually goes could be just 100 amp or maybe 100, maybe less. Okay. So that is the downside, right? And what about the IGBT? IGBT is actually the mixture in between the BJT and the this MOSFET. So it turns as IGBT, insulated gate bipolar transistor. Okay, so what's so special? BJT is it can actually handling quite high amount of this power, something similar to the BJT, but and also the current. However, the getting control is actually based on the MOSFET's topology. So it's a type of voltage control type of device, right? So that makes it a excellent device for power electronic converter drive. Okay. If you are talking about switching frequency, the switching frequency can be higher than the BJT, but lower than the MOSFET. That is the mixture. Okay, that come up with this guy here. Okay, the with the IGBT, then later on they do also come up with some different type. Okay, different variant. Okay. The last one is called the MCT. The MCT is called the MOS control thyristor. Okay, MOS control thyristor is actually the mixture between the MOSFET and also the GTO. So they have the mix in between the two, and hence you can see MCT is also a type of fully controlled type of device, and is also a type of voltage control type, as opposed to the GTO is current control type. Yeah, power handling capability is higher compared to the MOSFET. Yeah, switching frequency somehow higher a bit compared to the original GTO, but could be much slower as compared to the MOSFET. Okay, so those are the devices that I would like to introduce to you, because those devices, as I say, power electronic converter will only work with the switch. Okay, without the switches, the power electronic converter, just like a man without the heart, it cannot work. Okay, the blood cannot circulate to your body. Your hand, your leg also cannot move. Right. So this is what I wanted to present to you today. Yeah, for the this chapter 2. So far, any questions? No question. Well done. Okay, so I think formula. There are a lot of formula here. I only give you the when it comes to the test and also when it comes to the final exam. Yeah, only the general formula I will provide it to you. The general formula is actually inside your Google Classroom. You can have a look on it. Okay, the rest, the actual one, the actual formula, there will be no formula provided. You need to understand it and how to do derivation. Yeah, only then you can continue. Oh, oh, I used to be like that lah. Okay, this is the way I learned last time. There is no formula provided to me when I come to the this exam. Okay, so we need to half everything. Then only you can do. Yeah. One thing. The next chapter will be the chapter 3. The chapter 3 is actually the main content for this power electronics course. The first one is the AC to DC converter. Starting from there, okay, I will advise that you go back to the failure rate of this paper. It depends on the performance of the student one. I cannot tell you, like for example, last sem, I have only 8 students, but 4 main students, another 4 is actually from a small cohort, from small cohort lah, huh? Okay, so the main one, 3 out of 4 passed, but the small cohort one, those I believe they are actually left over from previous semester one. I think. So all fail. Okay, and but if you are looking into the last two, the next last 2 sems, I have quite a number there. I think it's about 40 something student or 50 something student. I can't remember. Basically, only 1 or 2 fail. The rest are passed. Okay, it depends. You cannot say that tak mau pass orang memang susah. Itu bukan susah. And it's not only for EE. It's the mentality of the student itself. I would say that. Okay, throughout so many years of my teaching, I can see if you are really putting your effort, then the chance for you to pass is very, very high. Okay, at least 99.99%. If you do not put your effort, definitely the chance for you pass, for you to fail, not for you to pass, for you to fail is also very high. Okay, now during my time, I want to tell you one true story here. During my time, okay, I am also graduated from TAR last time. Okay, of course, I study only up to the diploma kind of this level. Okay, I have only 1 exam for throughout the year. After I learn the entire year, then I have to sit in 1 time of this exam. So you can see all the notes, all the everything, all the subject add up is a lot. Say more than 10, 11 or 12 subjects per year, per exam. Also, if you want to, to promote or to upgrade to another level on another year, the next year, the higher year, okay, you have to actually pass all your subject. Okay, you have only one chance for a year. If you fail, okay, then you have to, the only thing that you do is you have to resit another year. The resit another year is not for that paper only, that you, the only paper that you fail. Yeah, for example, I'm telling you, if you have 11 paper, you got all 10 A or A plus lah, one fail. Okay, and then your this supplement paper also fail. Next year, you're not allowed to promote to the year 2 or year 3. Then you have to repeat the entire course. The entire course. Listen carefully. Entire course. Okay, all the subjects, including all those papers you already passed for A. You also need to repeat. So last time, we as a student, we are not afford to fail. We are not afford to fail. If we fail, bye bye to you. Okay. So you have, the only thing that prevent you from fail is you have to put more effort. Okay, in study. But now a lot better is a semesterized type of teaching formation. Yeah, one semester you take only 5 or 6 subjects, and the syllabus is also not really a lot, but of course this one is quite a lot lah. Okay, but I have already reduced. Okay, that's why I say it depends on the student itself. Okay, if you want to pass, you really need to put your effort in. Yeah, cannot 轻在轻在啊，轻在轻在，连有嘛澳洲轻在轻在啊。Okay, any other questions? We have 2 minutes more. All right. If no question, then I think that's it for today. So I can tell you that we have already completed our chapter 2. The next one is the chapter 3. The chapter 3, it may actually involve with this further series. Okay. Have you heard it? Further series? I believe you have studied the further series, right? Okay, you have the odd function, event function, and all those things, right? So please reflect a little bit. Okay. Up to you lah. But I don't like to record then restudy lah. Huh? Okay, you need to get it done so that you can understand and how to derive a given signal in Fourier series, and then how to find the value. All those things is very useful when it comes to this course. Yeah, you need to know those things first. Now, apart from that thing, and when it comes to the chapter 5, the chapter 5 is actually the AC to AC converter. AC to AC converter, that one, you may require to know this numerical iteration method, especially the Newton-Raphson iteration method. So please try to understand all those things. Okay, you need that skill, the calculation skill, in order for you to survive. Yeah. Okay. For the series, Newton-Raphson method. Okay. Please, if you don't like to recall, like Godwin say, okay, please restudy some from some book lah. Okay. So I think that's it lah. I'll see you next week. Thank you so much for your attendance. Bye bye.